Okay, thank you, thank you. Right. Okay, thank you. Because I was going to spend an hour talking and then realize much later. But I was just saying that the next thing that we are going to be discussing in this lecture will be the Zeeman effect. So it's similar to the Stark effect. The only difference is that the Stark effect came out to be much simpler because we didn't have to take into account the fact that the electron was spinning. So I only looked at the Stark effect only for n equals to 2. N equals to 1, I think it's simple. You can try to do the same trick that I did. You will have some z there, maybe 1, 0, 0, 1, 0, 0. This will be the first correction to the Stark effect for the ground state of hydrogen. Use the same. Actually, the ground state for hydrogen was not even degenerate, so you just had only to consider this term here. And what will this term give you? So you have to use the same argument I used previously in the beginning of the previous lecture. What is this? True is that that is the reason why I didn't do this one. So it doesn't matter what the ground state will be. So if this was, they have the same parity, this is odd. So this will be automatically be 0. So the first correction will vanish. So for the Stark effect for the ground state, you have to look at the second order correction. And another thing that I wanted to mention was just a bit of history that I skipped, but I did mention that the G factor for the electron was 2. So these results were actually recorded or reported in a conference in 1947. So what people did, let me just go back here, right? So we have discussed this effect. This effect we already know. This effect, although it's of order alpha to the 4, it's arising from the taking into account the fact that now the the the, the nucleus has a mass, and to do that you just replace that by the m that's appearing in equation by the reduced mass, which we know how to do. But the the nucleus also has a magnetic moment. So maybe if it was only the proton, it also has a magnetic moment. It also has a G factor, so it has mu I and Gi, and this, so it will also set up a magnetic field that will be felt by the electron. So you have to also include, so that will be called the hyperfine splitting, in contrast to the fine structure splitting that we had studied. But it will be of smaller order because of this m over p factor. So the only thing that is left in this table that I didn't mention was this one, which is called the lamp shift. That's a bit of history. So I think the lamp shift is one of the most important experiments of the last century. And what happened was that, so Dirac came up with this brilliant equation for the electron. And according to the Dirac picture, which I can't remember the equation off the top of my head. But in the next homework assignment, I will give the expression, but the point is that it only depends on J. So if you look at spectroscopic notation, I think it's this term P, I think, and also P half. I think this is 2P half. These spectral lines in the Dirac equation, I think there's MC squared plus 1, maybe there's a J plus half squared. But the point is that it depends on this J. Everyone is happy with this notation, right? So in spectroscopic notation, they define things like this. So you know that there will be a total angular momentum. This is orbital, so L, capital L, It can be 0, 1, 2, and is given by S, P, D, dot, 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 dot. But according to the Dirac theory of the electron, these two states were actually supposed to be degenerate. So although there might be some splitting that might be happening, but these two states were supposed to be degenerate. And what Lamb actually did was that Lamb and his student Rutherford, they actually measured these things, and to their surprise, they were splitting, which was contrary to what the Dirac picture or the Dirac equation was saying. So they had to explain, and not only was it splitting, they could actually even measure the change in the energies, which is what we have been trying to compute. In terms of the frequencies, this came out to be 1057, and it so that's not to go into the details of what I've in the lecture slides. If you click on figure hierarchy blah blah blah, I've included a link where I think Hans Bethe, who computed this number, actually he got 10 to the 50, 10 to the 40 heads. You can also calculate, you just make use of the E2, know how E2 will be H and N, make use of that E minus E N with K, maybe N and K. But it's a 3-minute video, and Bithe is one of the people who first, it's a back of envelope calculation. So I just thought I should mention this lump shift. Now let's go back to the Zeeman effect. So there are 3 cases for the Zeeman effect. So either you have a very strong magnetic field, a weak magnetic field, and an intermediate one. So depending on the strength, so without any magnetic field, right? So these are the usual spectral lines that you might get, maybe the Balmer series, Lyman series, or whatever. But once, depending on how your magnetic field is set up, these lines will split differently. So there are 3 cases to consider. The first one that I will be considering will be the weak Zeeman effect. So weak in comparison to what? So there will be the external field that you set up. But remember that when we're looking at the fine structure, right, you have the electron, which is a charged particle, but it's moving around a nucleus. So it also sets up some internal magnetic field, which is what I calculated. The thing with the 1 over c squared v cross dv over, this was the internal magnetic field due to the motion of the electron relative to the nucleus. So you have to compare B internal with B external, and depending on which one is bigger, so let's say that B external, which is the weak case, which is the one that I'm looking at, if this is very, very tiny in comparison to this one, then the Zeeman term, which will be minus mu B external, we still have to figure out what this mu will be. This is just B external. If this is weak in comparison to all the other terms, then this will be your perturbation. So you have to find the correction will be due to this one, meaning that you have to find good set of quantum numbers to diagonalize the Bohr Hamiltonian together with the fine structure constant. And these good quantum numbers are the usual. It's J and MJ. They are good quantum numbers to diagonalize this part. So you only have to worry about what will be the contribution coming from Z only. Whereas if it is the other way around, if it happens that the magnetic field is the one that is actually very dominant, the external one, then this term then will be the perturbation, whereas this one will be dominant. That will be the strong Zeeman effect. But if these two magnetic fields are of the same order of magnitude, then you have to go directly and use what will be the one degenerate perturbation theory. So for example, for I think I did for n equals to 1 or n equals to 2, I can't remember, but it would be, I think, 9 by 9 matrix that you have to diagonalize. For n equals to 2, maybe 3, you will have to diagonalize the 18 by 18 matrix. So I think for today, if I can only go through the weak Zeeman effect, the strong Zeeman effect, the intermediate one might be too long. So yeah. Right. So the magnetic moments, there are two of them. So this picture works, but you shouldn't take it literally. So you have an electron that's about the 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 nucleus. So it will have some orbital angular momentum, which will be called L. And with this orbital momentum, there will be an associated moment in L. Similarly, the electron is also orbiting about its own axis, so it also has some S. So if you remember the equation that we defined, classically you know that E will just be given by Q over 2m multiplied by, which should I use for angular momentum? Let's just say L. And even in this case, quantum mechanically, you still get the same result. However, for the electron, there's a G factor. So G factor, and this is called anomalous magnetic moment of the electrons 2. So then you end up with 2, the 2 cancelling that 2, so you end up with minus over ms. So the total magnetic moment will be due to the one due to the angular momentum, the orbital one, plus the one due to the spinning electron. But they differ by a factor, by this G factor. So when you write everything down, you have to dot B. This will give you Hz multiplied by E over ms plus E over m. Let's say there's a minus, there's a minus with plus, and L. And this has a 2. So you can factor out this E over 2m. So let's just say you have E over 2m, there might be an H bar, and then you're left with L plus 2s. The 2 is coming, basically the G factor for the electron. So you have L plus 2s, and this is what you want to diagonalize. If B is smaller, so this will be for weak fields, then the fine structure dominates, and then Hz, what I said previously, so your perturbation will be given by this one, which I derived. That the 2 I repeat comes from the anomalous dimension of the electron. And I have to repeat over and over, it's not true. Even though the Dirac equation is a brilliant equation, it gave you, tells you that it's not true. And when you calculate it, I didn't write it down. When you calculate it, it makes this stuff that we're doing, it's one of the most accurate theories in the whole of science, because the number that you are going to calculate with Beaver or the others only calculated only the first order, yeah, it's very precise. I think the matching, the last time I checked, might be 1 part maybe in 10 to the 12th of matching between the experimental value and the experimental. But for today, I think we should just take it as true. Right, so we have to find the good quantum numbers for these ones. As I said previously, the good quantum numbers to diagonalize this Hamiltonian will be J and J. And this So we only have to figure out. So basically, we have to figure out what is this L plus 2s, because this is just using first order perturbation theory. It's just the expectation of these operators. It's if I put them like that. Now, the total angular momentum was the one which was conserved, but it's being made of two things, L plus S. So as they actually precise keep changing, but to find the average, it seems as if the average will be the projection of S. This will be S, the projection of S on J. So we've done this before. It's just given by S dot J over J squared J. This gives you the average value for S. I'm not that happy with this derivation. It's just this one. Right? So I managed to find, if you look at Griffith, it's given as an exercise, so you have to use what is called this Wigner theorem, which requires you to know something about symmetries, which I prefer to cover in the last lecture. So I have my own, it's not really my own derivation, but basically I want to derive this vector. I'll do it very quickly. So this slide that doesn't. Okay, so might have to use the whiteboard because I don't want it to be too cluttered. I'll come back to that if you don't lock me out. Share whiteboard. Remember that we have chosen our good quantum numbers to be J and J. So the first thing that you check with some operator, this could be a general operator, let's say A. So you find the commutator between J squared and A, find the commutator between J. So this, I took this from F. Mandel textbook on quantum mechanics. It's just called quantum mechanics. But okay, I'll try to be quick. So you take that commutator, and it's given by energy. Maybe if we have during consultation, I might show you how to get the identity. Given by 8 bar J squared A plus A J squared minus 4 H bar squared A dot J with J, right? So if you chose, and this holds in for generic operator. So if you take A to be Z, so then you look at, let's say that you define this thing here, where we're taking this to be as Z, and then you chose this to be, let's say, let me just call that X. And so X will just be J squared as Z. Then you look at overlap, say J M J squared as Z, not maybe with X, let's start with X, right, where X is given by that, and then you have Jm, right? So this will give you Jm J squared. Everyone is agreed, this is just a commutator, so it gives you J squared X minus X J squared Jm. Right? J is emission, so it can either act there. This gives you x j 1 minus, and when it's there, it gives you j plus 1 with the x, but these are just numbers, so you end up with x j minus the same thing. So this is 0. So it means that if I were to take the expectation value of this thing jm with jm, it should get 0 because of this argument that I gave there. So so have that expectation, that expectation, that, and this is what I'm looking for the Zeeman effect, because this is something like s dot j z on j. Right. This is the operator that I'm looking for, and these type of things I know how to do. So I end up with, let me just remove everything. So plugging it into that equation, 2 h bar squared jm t squared sz plus sz t squared jm plus 4h bar squared j s dot j. I think this is j set jm, right? And this will just give you 2h bar squared j plus 1, right? This type of operations. Maybe m, this will give you 4h bar squared jm s dot j, and this gives you an m, which is half jm. And then you should be then able to solve for what this operator is. I'll include this in the slides. It's just in the slides that I have now, I didn't write that down, but I'll write down the argument and I see. This is what I was afraid of, so okay, let me try this once more. Stop sharing. Okay, now I can share the slides again. Okay. But the point is that in order for you to do the strong or the weak Zeeman effect, you have to find what is the expectation value of S J in the bases where they are not orthonormal. So you have to do a lot of work to find that expression, or you can just do what Griffiths did, which is just to say that, well, you know that J is conserved, the vectors S and L might be changing, but they precess. So if they precess, you just, the average, time average of them will be the vector, the projection of the vector along there, which ends up giving you that, which ends up giving you that S expectation will just be given by S dot J over J squared J, which is what I've just shown, because if you remember, you ended up with S dot J was being sandwiched between Jm and Jm. This ended up giving you something like J squared with S, and yeah. But I will write the full argument. So in the slides that I will give you, I think after this equation, there will be another slide where I derive it using that method that I tried to explain. But the point is that you do the same thing that I did for L.S, right? So remember that L.S, how to get this operator, get the total angular momentum was L plus S. If I squared J squared, I ended up with L.S, but now I'm not looking for L.S, I'm looking for S.J. So let me look at L instead. L will be given by J minus S. Then I square everything. So when I square that, I get L squared will be given J squared plus S squared minus 2J dot S, which is what I'm looking for. So I can solve for what is this S dot J, given by half J squared minus S squared plus S squared. This, then I can try to find the expectation value. This just remember that the expectation value J acting on Jm gives you H bar squared. So this will introduce this one, J times Jj, which is coming from this operator. Same with L, same with S. Right. Then plug it into this term. I think the expectation of L might be processing, maybe this is S, this is L, might be approximately the same, so you get that one. This term here you get from the, so you get that term from this, which we got out there. And the term in square bracket was known for the Landé factor. So the expectation, this expectation will somehow depend on, we just call this constant J, which would be, it depends on the total angular momentum, the spin, also the orbital angular momentum. We just call it Gj, and this expectation will give you some Mj. So the final result for the weak Zeeman effect is that your spectral lines will shift by an amount which will be given by mu Bohr magneton Gj. Gj is what we've been trying over this laborious thing, finding S dot J, finding the correct, finding the expectation value. All that we did was to try and find this number Gj. We have and then there's this Mj, the X. So this is the final expression. So let's try and look at the simplest case. So the simplest case will involve n equals to 1, L equals to 0, J equals to half. So for this type of things, you have to find the Landé G factor. So you have to calculate that. But the total energy, so the total energy is given by the fine structure energy, which doesn't change because the term, the Zeeman Hamiltonian is the one which is much smaller, so the fine structure being treated as a perturbation too. This doesn't change, so it's the same result that I got previously. It was n, this factor, right? You will have an alpha squared, I think 2n squared. This is 3 minus n over j plus a half. Right? So the total energy will be due to, you still have to find what is the fine structure energy. It's given by this expression. So for j equals to half, this gives you 1. So I think this is a 3 over 4. Just check. So we get that the energies, the fine structure will be given by 1 plus alpha squared. This gives you 3 over 4. J's, in this case, J is half. This gives you 1. 3 over 4 minus 1. I think that gives you 1 over 4. Only 1 over 4. So this gives you this energy. which is this. But you still have to find this energy which is due to the Zeeman effect. So to do that, you only have to, like, mj goes from minus mj to mj, so you'll have two sets. So either mj will be a half or it will be minus a half. So this energy is plus or minus. Right? And the g factor, let me just see, L is 0, J is half. Okay, let's do this. So this is 0. J is a half. I think S is also a half. So this just gives you 2, which cancels that term there. Saying that for J equals to half, J times J plus 1 is the same as S times S plus 1. So you just get out of 2, cancelling that 2. That cancels that. Not sure. Okay, we'll have to check, but I think it comes out to be true. So this means that your energies, you end up with two sets of energies. It's to be the minus 13.6, 1 plus. Don't worry about the G factor. I think in the next example that I will calculate it for these type of states. So you end up with, so you first calculate the fine structure contribution, you get alpha squared over 4, and then you get plus mu. This was given by 2 factor of 2 b, and mj was just a half. So I think you end up with only plus or minus mb, mu b. This is Bohr magneton. So if you plot, and then you can plot these energies. So you start with something that was generate, right? And once you put this into an external magnetic field, remember that we are plotting E is given by, let's go cos number C, which is the intercept, plus mj mu b x. So as you, so the mu and b are your variable. This is just a constant. So mj chose j to be half. So once you calculate everything, it's either going to be plus half. So you get some line which will have positive slope of half, and another one which will have negative slope. And this is the energy diagram that you get for the weak Zeeman effect. Let's say now if you have 8, so that was for n equals to 1. So for n equals to 2, there will be 8 states. So this is similar to the stack effect, n equals to 2, n equals to 2, and then remember that j is given by L plus S, so it's plus or minus a half. So L can be either, you get 1 or 0. So let's start with the states with 0. So you get 0, then you get half, or half and half, 0, half and minus a half. Then you get states that will have, so I'm labeling this as, this is L, then this is, so then there will be states which will have, and this is J. So 1, can you do the same thing, half and half, 1, I think this would be half and minus a half. This is another state. And then you get the states which will have 1, I think it's 3 over 2. Then they will be ranging from, then MJ will be ranging from minus 3 over 2. There will be the state. Then there will be a state with minus a half, state with half, and state with 3 over 2. So these are 4 states. These are 4 states. So you end up with these 8 total. In total, you have 8 states. And remember, you want to draw a diagram similar to this one. You want to see how this degeneracy actually gets to be lifted when n equals to 2. So you have 8 states, and for each state, you first have to remember that your formula, the total energy, as in this diagram, will come from defined structure and also Zeeman effect. Now the fine structure one you can compute, so you just get E. I think for these 4 states, you use the final formula that I gave in the last lecture, so you get something E n squared 1 plus alpha. I think it's 3 minus n over j plus half. And when you work everything out, these first 4 states, you get like do it some more. Let me just clear everything. Right. So remember, for this type of problems, you just have to find the fine structure. Right. So for just 4 states, you get that the fine structure is going to be given by minus divided down 3.4 1 plus alpha squared over 4 2 over 1 minus 3 over 4. You just plug the plus a half. So for these days, I think j was half. It's half plus half, which gives you that number there. And once you simplify everything, you get minus 3.4 electron volts. The electron volts coming from the n squared, right? I'm choosing n to be 2, just minus 13 divided by 4 will give you that. And then the thing in brackets with 1 plus, this works out to be alpha squared over you can do this, it's just some number. It will be reported in the next table. Then you do the same thing for the remaining 4 states. So E fine structure, this one will have to be 3.4 1 plus alpha squared over 4. Let me just look at the table because I didn't work them out. So what I was saying, that you will have these 4 states which will have these energies, then the remaining energies. This is not E and J, this is just the fine structure. And then the total energy, now you still have to find the one that is coming from the Zeeman effect. So this one will be given by, there's a GJ, where this GJ is given, Landé effect is given by 1 plus, there's going to be J plus 1. You can compute them. This is just the numbers that you get. Put them into that formula, the external mu. And then for every value of mj, you will get a different thing. So, and then if you wanted to plot them, so these are the energies, fine structure energies, which will correspond to you when you set the magnetic field to be 0. So the hydrogen atom for n equals to 2 was highly degenerate. Once you have start applying this magnetic field, so you're basically putting the minus 3.4, 1 plus alpha squared over 16. This is a constant plus g factor, which you calculate, which will give you the slopes, right? Then mu b external. So this we're treating as your x. So get y equals to constant plus some slope plus x. So this will end up giving you this 8 lines. So it seems as if we'll say that your general system should be completely lifted for this one. Unlike the one for the stack effect, for the electric field, we still had something like En4 was equals to En3. So it was not really completely lifted. But once you put this in a magnetic field, it seems as if everything has to be lifted. You can try to do this n equals to 3. Right, so you get things like 3, you split your L, so L can be 2, L can be 1, L can be 0. So you end up with having to look at states like 3, 2, 1, 0. And then you also have to consider them with MJ. So find what is J and what is MJ. Form this set of, basically you repeat these type of things. And I think this is just a summary of how these things split. So for the week, this is for the week. You start with some states, and for each value of MJ, you get a different. See, for every value of MJ, MJ will be varying between minus J, 2 plus J. So for every one of them, you get a new spectral line. Similarly, for the states, remember that J is given by L plus or minus half. Now for the strong Zeeman effect, I think is much easier because remember that, so in this case you have that the external is much bigger than the internal field. So this means that the fine structure is the one that is the perturbation. So you have to find a Hamiltonian that will, good set of quantum numbers that will diagonalize H naught plus H Zeeman. And this set of quantum numbers will be the ones which are labeling these states. So I'm saying that this is part of your H0. So the states that we have to use will be N, L, ML, and MS. And in these states, if these are good quantum numbers, then this, once you diagonalize this just gives you MS, and this gives you MS and ML. Right? But now you have to find what is the perturbation. Okay, let me summarize. So for the strong Zeeman effect, the perturbation is not the Zeeman Hamiltonian, is the structure one. But we are not using the basis that I used previously, which was just N and N, J, and MJ. Now we have to use this set of quantum numbers, so we have to figure out what this will be. So it's claimed that HR doesn't change. The only thing that changes is this. The other way around. Okay, this doesn't change. So if you look at the, what am I saying? SO is the one that will be changing. So SO has a term like L dot S, right? So in this basis, this just works out to be, if you want to do it properly, you want the expectation of that. Now the expectation of L in general, X is not diagonalize it, but the expectation is 0. You can write this in terms of L plus and L minus. Right? Lx is can be written as L plus as a linear combination of L minus and L plus. So if you say you wanted J with M, the problem is that when L plus X or JM, it changes this thing. So you might end up with JM, J plus 1 or something. It's a different state, and these states are orthonormal. So this ends up giving you 0. So this expectation values are 0. These ones are 0. This one just gives you H bar, S. For LZ, you get H bar, L. So expectation value for that just gives you H bar squared, MS, and L, which is this one. The L times L plus 1, these are just coming from you finding the expectation value of 1 over R cubed. So nothing changes. The only thing changes is that now you are not using these eigenstates. You are using the ones being labeled by ML and MS, and the eigenvalues are just ML multiplied by that. So once you plug that there, so this would be the term. So this term doesn't change. This is the one coming from the relativistic correction. The one that changes is the one coming from the S spin orbit coupling. And once you add them, get that final expression which is at the bottom. And you can do the same thing. So for the 8 states that are considered previously, which were these, okay, now one has to be careful. Yeah, you have to first find the fine structure constant, which changes, and you also have to find this one, right, which would be different. So the point is that for the strong one, you're not calculating G, you just calculate the sum ML plus MS, because this is your energy will have a term that, so the Zeeman Hamiltonian, once you can diagonalize in this basis, so we just get ML plus, I think it's 2MS, part of the Hamiltonian, so you have to calculate these numbers instead of calculating JG, then find the fine structure, then just add these two things together. The numbers will be different, and then you can draw the similar type of diagram, right? So in this case, you have mu be external, and on the other one, so you start with energies that were degenerate before, but now will be different. I think this diagram that I still have to improve, which will show what happens for the strong Zeeman effect, and then this is the splitting for the Zeeman effect, which is obviously different from the other one, which ties with that picture. So if I gave you that picture with the circle in the beginning, without magnetic field, they don't split, but depending on whether you apply a strong or weak field, they split differently, which will be explained by this diagram. The next one would be the intermediate one, which it will require a lot of work, because we first, okay, I'll stop here, but just to summarize, the first thing that you have to do for the intermediate Zeeman effect is that you have to make use of the full degenerate perturbation theory, meaning that the first thing that you have to do is that you first have to change bases. So you have these vectors Jm. Now you don't know which ones, whether these Jm's are the good quantum numbers, or whether the ones that I was using, which is Mj, is Ml, or Ml, Ms, whether these were the good quantum numbers. But you just write them as linear combinations. So you know that Jm will be given by, you insert a 1. So this 1 will be the original vectors, which will be J1, M1, J1, J2, J, let's just call them alpha, 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 and then we hit this with Jm. Right? So like what I did yesterday, this is a C number, so the other way around, so you get that you can have J and alpha with these coefficients J and alpha, Jm. These are just constant C numbers. So basically, you have to find the Klebsch-Gordon coefficients. I can't write Klebsch-Gordon coefficients. Change basis from Jm to, it's labeled. You also have to include this S and ML in the labels. But this is what I will do in the next lecture. Much more complicated, and it will take too much time just to get these numbers. So you do that, and then you have to somehow try to diagonalize this matrix, which is what I will do in the next lecture. So I think I will stop here. Are there any questions? Then I think we can, if people want consultation, I was suggesting that you can consult me on Fridays. I think the time that works for me would be Friday, I think between 4 and 5 p.m. So everyone happy with that? Meaning that I will leave the discussion or course room open, then you can ask. But I think if maybe this week, if no one has any questions, then yeah, we'll see you on Friday. I think I'll stop there. Okay. Okay, then, okay.